So in this example of Gauss's law, we're going to consider cylindrical symmetry. And here we have a long cylinder which carries a charge density that is proportional to the distance away from the axis. And that's given by rho is equal to Ks. Okay, so the electric field here is going to be pointing outwards. Okay. And if we just write down Gauss's law, so we have our surface integral of E dot dA is equal to the total charge enclosed over epsilon naught. So what's the first thing we do? Well, what we're going to do is draw our Gaussian surface, which is contained within this cylinder, because we're looking for the electric fields inside the cylinder. Okay, so here's our Gaussian surface, which is going to be centered along the axis. This is going to have a radius, which I'm going to call A, and it has a length, which is given by L. Okay, so this is along the axis. So what is the total charge which is contained within our Gaussian surface? Okay, well, our total charge is just going to be given by the volume integral of our charge density. Okay, so we have total charge enclosed is equal to the volume integral of rho times d tau. And d tau in a cylindrical coordinate system is given by s ds d phi dz. Okay, so now we must integrate this for our limit, which is going to be between 0 and a, 0 and L, and also 2 pi. So what we have is the total charge enclosed will be equal to a triple integral. For Z, it's between 0 and L. For phi, it's between 0 and 2 pi. And for S, it's between 0 and A. Rho is given by Ks, so we have Ks by S ds d phi dz. Okay, so we just need to work out that integral to find the total charge enclosed. So the total charge enclosed, when we work out the integral, for phi and for z, it's going to be 2 pi L by K. We have S squared, so we're going to have S cubed over 3, and this is going to give us A cubed all over 3. Okay, so that's the total charge now that is enclosed. Okay, so I'm just going to write it out a little bit neater. So you get 2 divided by 3 pi L K A cubed. Okay, so that's our first step. Now, symmetry dictates that the electric field is going to be pointing really outwards. Okay, so for the curved part of our Gaussian surface, we're going to have our integral of E dot dA is going to be equal to what we've just calculated here. So But first of all, we know that it's pointing really outwards, so the magnitude of the electric field is going to be constant over the surface. So E can be taken outside, so we've got E, which is our electric field magnitude, by the integral of dA, which is just the surface area of the cylinder. When we do this integral, we have 2 pi AL by electric field. So 2 pi AL by our electric field. Okay, so that's one side. And what this then is going to be equal to is what we calculated up here. Okay, so just have to put these two together. So now what we have is 2 pi AL by our electric field is equal to 2 over 3 pi L K A cubed. So the electric field, so 2 is going to cancel, pi is going to cancel, and A is going to cancel, the L is going to cancel. It's going to be equal to 1 over 3 by K A squared and it's going to be in the S hat direction. Epsilon naught.